at one particular composite rotation, namely the corpse rotation. Just to give you an example, the corpse rotation is 3 successive rotations. First you do a rotation around the 2 axes. This is this little red trajectory here by 60 degrees. This is if you want to do a pi rotation. Well, corpse actually works. You can put together any rotation on any axis, and there's a recipe for doing so that's given in the first of the papers that I cited. Anyway, here to do a pi rotation, you start out with a little rotation around the 2 axes by 60 degrees. If you have a little tuning error, you don't stay in this plane here, you make a little deviation. The second rotation, 300 degrees around the -2 axis, except your torque vector is off a little bit out of the equator again, so you have this slanted trajectory. And then you do a 420-degree rotation around here, and you end up at the North Pole. You can see this is a bit closer than here. So if you look at the excited state population during this, you can see sort of a funny evolution over time, and then bang, you get close to 1. Oops, let's see. So this is what you see if you try to compare that to a plane pulse, just a single pulse, as a function of the tuning error, and this is indeed data that we took in the same experiment that I showed you. So you can see the plane pulse gets good fidelity right on resonance, but it drops off as soon as you go away from perfect. Whereas the corpse pulse, in a fairly wide region around 0 to tuning, is very robust. What we can also do is we can do back-to-back corpse pulses. We do this, and then we do it again, and then we do it again, right? And we could compare it against just regular Rabi oscillation, but instead let's compare it to the rotary 2-pi echoes, because those were also very robust. And you can actually see in this particular experiment that the corpse pulse decays about as fast or as slow as the rotary echo, which means in this particular experiment, it completely corrected for the tuning spread, and we were just left with decoherence. And you can look at the excited state population after each of these composite pulses and see how it decays over time, similar to the data we saw before. And you can extract the fidelity for a single pi pulse. What we found in this particular experiment was, disappointingly, it was not very different from a plane pulse. And this illustrates another important point about robust control. This, when you sweep out this huge angle overall, takes much longer than a plane pulse. So there is more time for things to go wrong if, for example, you have decoherence ticking in the background, and that's what we had in our experiment. So this, in the end, didn't buy us much. If we had had much less decoherence in this particular experiment, the gain from the corpse pulse would probably have been substantial. Okay? Yeah.
The Rabi frequency is the same for the plot as well?
Yeah.
It's just...
Yeah. I mean, it's an important point that if you might say, well, why don't I just increase the Rabi frequency so that this takes the same time as the plane pulse? Well, that wouldn't be a fair comparison, because if I turned up the Rabi frequency for the plane pulse so it took a shorter time, then that would work better too. Right? In these controls, you usually turn your Rabi frequency up as high as you can to overwhelm any detuning errors and to make it fast so you don't get as much decoherence. You always go full throttle on your rotation rates. Okay, so that's an example of a composite pulse. You can do the same for the other 2 pulses, and you can see that they buy you some robustness, for example, in deviation from perfect Rabi frequency. So very effective error compensation, but extra decoherence during the longer sequences, pulse sequences. Nevertheless, I think if you're doing experiments with ion traps or doing quantum simulation and optical lattices or something like that, it's useful to know that these techniques exist if you have to do perfect spin manipulation under less than ideal circumstances.
So what was BB1 trying to address? Corpse and Scrofulus addressed different aspects. Was BB1 trying to do both at the same time?
I think BB1 was trying to get the same robustness as Scrofulus against variation in Rabi frequency, but not as much penalty for variation in the tuning at the same time. That's my understanding, I mean, if you look at the sweet spot.
And that central sweet spot that you showed us was what for fidelity?
Oh, I forget exactly. Yeah, they had a funny way of calculating it in that paper. I mean, normally I would say, if you're trying to do a pi pulse, the fidelity is the overlap norm squared of the state you make with the state you want.
Yeah.
They had a slightly different fidelity. I mean, they were, you know, because that's the fidelity for a particular initial state, you have to think about the fidelity of the overall transformations. But again, they have a funny way of doing that. I'll show how I think that fidelity should be defined. Okay. Composite design. What are the limits? Well, not surprisingly, it has been people from the NMR community that has pushed that also. Here's another pair of papers where they looked into design of arbitrary excitation profiles. We're making these sweet spots look whichever way you want as a function of some parameters that they could modulate about the pulses. And these parameters, as a function of time, would be computer designed. So we already heard something about how you do numerical optimization of control waveforms in Ivan Deutsch's lectures. But here, just to remind ourselves, here's the general idea. Okay, so for these qubits, we have a sequence of rotations, which make up an overall unitary. For each of these rotations, what we specify, well, there's an axis and there's an angle, but these are described by the phase of the microwave field and the Rabi frequency time product, that is the rotation angle, for the first pulse, and so on and so forth. So we can put all these parameters together in a vector, and we can define a cost function, which is the difference between the unitary we make with those particular parameters and the one that we want, norm squared. And just to remind ourselves, what's the norm of a matrix or an operator? Well, it's the trace of the matrix Hermitian conjugated with itself. Right? That's how you define the scalar product between matrices. Matrices make up a vector space with a scalar product as well. That's how it's defined. So that's what we want to minimize. We really want to minimize the difference between the unitaries. And so the idea is you break out MATLAB or Mathematica or something like that, but there's a numerical minimization or optimization routine. And you minimize this cost function here as a function of these parameters. The key now is that you decide what this cost function should be. Right? And so it doesn't have to be that you just want it to work perfect over some interval. Maybe you want it to work perfect over some interval and not at all, or do something completely different over another interval. So these are sweet spots that these guys could engineer. You see, this composite pulse, which was some very complicated phase modulation as a function of time, worked perfectly over a very wide range of detuning. But in terms of Rabi frequency, it had some sharp region where it worked perfectly, and then it dropped off to zero and did nothing at all outside of that. So kind of like a window function or top hat function. Here the top hat has been turned the other way. Here the top hat is at 45 degrees, so this works perfectly for certain correlations of Rabi frequency tuning and not at all for others. Here the sweet spot spells out JMR because they wanted to publish this in Journal of Magnetic Resonance. So that really shows you how you can engineer the shape of your pulses. Right. This, I think, is actually an NMR experiment where they read out the fidelity of their pulses. So obviously you can do a lot of stuff.
And do you know what are the axes? I assume these are axes.
It's the same as before. This would be the detuning axis, and this would be the Rabi axis. It doesn't actually make any difference. You can design things to look whichever way you want, as long as you give yourself enough pulses, a long enough control sequence. There's a lot of information in something like that, so obviously you need a lot of free parameters to fit your response to the right shape. Okay, so this is obviously more on the conceptual level, right? Hopefully we're comfortable with the idea that computers can help us do this kind of magic. And so I get to the last part of my talk, namely the application of these ideas to resonance imaging and addressing in optical lattices. And this is where, as I said, I have planned to take off my teacher's hat and put on my research presenter's hat. I don't think, so we've gone at a careful pace with time for questions, and that's good for a lecture. So we'll see how much of this I can get through. Fortunately, Jae-Hoon Lee, the student who did this experiment, will be in the lab tomorrow, and you'll be able to talk to him and get details and so on. And if we leave something unfinished, we can always continue on Thursday. Any questions before we launch into this second part, a third part actually? Okay, good. So, we have, I think, already had talks on neutral atoms and optical lattices. I know that, didn't Marcus Greiner give a lecture yesterday? Yeah. So this is an idea.
And we have the most incredible animations, by the way, so you have a tough shot before.
There's no way I can compete with Marcus on that, or many other things. And that's indeed what I want to talk about, is if you can't compete on just making things work incredibly well, then you have to rather make things work robustly in the presence of imperfection. That's much more my specialty. In any case, so you should be familiar then with the idea that you can use atoms and optical lattices to do quantum simulation of thin-dimensional physics. There are proposals out there to use the trapped atoms as qubits for a quantum processor. There are proposals out there for using atoms and lattices as atomic clocks. These two in particular, well, one can debate the degree to which they require it, but they would certainly benefit from the idea of reaching in and touching, imaging, and addressing atoms with single-site resolution. So, well, we have the optical approach, Marcus Greiner's beautiful quantum gas microscope, which you can combine with the idea, if you send a laser beam in through this microscope and focus it on one of these atoms, the trapping potential in the lattice, which is this egg-crate pattern, you might aim a tightly focused laser beam on a particular atom, and then if you choose the polarization of that laser beam correctly, maybe you can cause a relative frequency shift of the two qubit states just for that atom. And then if you shine microwaves on them, they would be resonant with this guy here, but not touch any of the other ones. And this was done in experiments by the group of Emanuel Bloch some time ago. Tightly focused laser beam, microwave shining on, and flipping the state of just one of these atoms. Now, as I said, our specialty is not doing things perfectly, but being a little bit off. Okay? So, suddenly in these experiments it's a challenge to have control over pointing errors of this focused laser beam relative to your atoms, because if you're not hitting that quite right, the frequency shift of this qubit is not quite right, and then your microwaves won't do a perfect spin flip. Okay, and even in the Emanuel Bloch experiment, I think they have some trouble with this, because they had a very high-powered real-time algorithm for looking where the atoms were and adjusting their focused beam accordingly, I believe. And even so, they were limited to do what's called adiabatic spin flips, which is another robust way of going from up to down if you're not quite sure where the resonance is. So that's the kind of problem we can solve with the tools of robust control. So let me talk about the experiment that we did. It was a three-dimensional optical lattice experiment. We put cesium atoms in it, picked these two stretch states as our qubit, and then to create spatially dependent stark shifts, or light shifts, we didn't use a single focused laser beam, we used a one-dimensional standing wave, so beams coming in at a shallow angle and interfering with a large period along x and creating planes of constant intensity in the YZ plane. Right. So if you look at the lattice sites in this lattice along the x direction, they're half an optical wavelength apart, and then you get a light shift, relative light shift of these two states that varies in space. So these red dots mark the lattice sites and their the shift of this transition frequency as you go along the x-axis. That's the kind of situation you can create here. So there's a couple of things that I'll go over very quickly just to help you understand what you see in this experiment. Here's the situation again, sort of ideal alignment, right? The lattice sites, the spatial shift. We've got well-defined frequencies where these atoms are resonant. So if I do a microwave spectrum where I measure as a function of microwave frequency, see, we can do movies too, right? We see that there are resonances at particular frequencies, and this well-resolved peak corresponds to these atoms that sit in the middle here. Of course, things are not perfect, at least not in our lab. So typically the angle of the lasers that make the standing wave are a little bit off, so the two lattices are non-commensurate. Right? So if you have an atom right at the top here, the next one will be a little bit off. Right? So once you look at the resonance frequencies for all the atoms in this lattice, if it's extensive in this direction, you're going to get a continuum. And the other problem is that maybe the lattice planes that trap the atoms, the ones in the direction orthogonal to x, don't quite overlap with the lattice planes, or the planes of constant intensity in this 1D standing wave. Right? So an atom sitting here has not exactly the same light shift as an atom sitting on the other side here. That also makes things less than ideal. So once we take all that into account, here's the x direction, here's the y direction. This shows the position of the lattice sites in the xy plane. They sort of get twisted around in odd ways. And if we do what we did before and look at a microwave, take a microwave spectrum, we really get a continuum. Stop this. If you scan that out, you can see no matter what the frequency of my microwave is always atoms that are resonant. Actually, it's not a big problem because what you can see here is, if you look at the edge here, we have one optical lattice. Every atom has a neighbor, half a wavelength on either side. If you look at the next row over, it's exactly the same thing, except it's been shifted. That's exactly the kind of error I want to be able to compensate for if my large period standing wave and short period standing wave has a phase that's not accurately controlled over time. So here I'm just having a whole ensemble at once of all the different relative lattice positions. And that's really what I want it to work for all different relative lattice positions I'm trying to do. So this is not a bug, it's a feature. Anyway, let's put that aside for the moment. Yeah.
So, what's the difference between trying to address single sites using these light shifts versus applying a magnetic field gradient?
It's very much the same thing. As a matter of fact, what we do here is we design the light shift to act as a fictitious magnetic field. Okay, but we can make the gradient a good bit steeper than you can with a magnetic field.
In terms of the errors, would working with magnetic fields be easier?
It's hard controlling very large magnetic fields accurately, and in particular, it's hard switching them fast. You know, I do think it depends on the context, but I would not want to have the necessary magnetic fields around in the kind of experiments that we like to do with these atoms. Light is easy to turn on and off. Okay, how can we use this now to address atoms? Imagine that I apply a pi pulse with a certain frequency bandwidth, which is 1 over the pulse duration, tuned exactly to these atoms here sitting near the middle of the sine wave. I can apply a pi pulse to those. So if I originally started the atoms in the upper hyperfine state, they would end up in the lower hyperfine state of the 2 qubit states. Okay, so change the internal state of some selected atoms. And then I can use radiation pressure to push these guys away by shining light on a transition that starts from this state, but would be off resonant if I start from this state here. So these guys are gone. So what I've done in 3 dimensions is I've prepared planes in the xy direction, in the yz direction. In the yz plane, the x direction is along here, and I have them periodically in space. Now that I've made these guys, I've initially prepared atoms in f equals 3. All the others are gone. I can image them using the same trick. What I can do is I can leave this long period standing wave in place, or the superlattice as we sometimes call it, and apply a second pi pulse and measure how many made it from f equals 3 back into f equals 4. and I can plot that number. Then I can spatially shift this standing wave by a little bit, say using an electro-optical modulator, and I can do the same trick. But now this guy is a little bit off in detuning because it doesn't sit at the sweet spot in the standing wave. So I don't transfer as many to f equals 4. And the next step I'm completely off. You can see I could do this on the other side as well. And I could make a resonance image, and this is what it would look like. And you can see we can do far better than we could do with an optical microscope. Right? This peak here has an RMS width of 80 nanometers. That's pretty good. And it's really just determined by the spectral resolution that you can do in your spectroscopy. So spin control can help you image things. That's pretty nifty, I think. Of course, we're not by any means the only people doing this. The idea of doing resonance imaging is very old, and you've all heard of MRI, magnetic resonance imaging in medicine. This is basically the same idea. We can prepare many planes by shifting this long period standing wave around. Because we flip some spins at certain positions that we want, blow the rest away, and then we image them. So it works that way. But as I said, we are not always perfect experimentalists. Sometimes we have errors. How much time do I have?
You have about 10, 15 minutes. 10,
15 minutes? Okay. I can probably say something close to what I want to say about this experiment in that time. Okay, so in a real experiment we have magnetic field errors. Okay, and these qubit states that I showed you are sensitive. The separation between them will oscillate with background magnetic fields, for example. We do have errors in microwave frequency and microwave power. Actually, the error in microwave frequency is not so much that we don't set the microwaves to the right frequency, it's that the transition frequency depends on magnetic fields and also the light shift in the lattice and so on, which can be heterogeneous. And finally, the relative positions of the lattice and this addressing wave can change over time. They may not have the right intensities either. So there are errors that basically cause the position of these points to jitter up and down. Right? And that would give me trouble with a microwave pulse like this. So what should I do? I should, of course, make one of these designer composite pulses that makes a perfect pi pulse over some frequency range that spans about half the distance to the neighboring sites. Right? Then these guys can jitter around by a maximal amount. And then, of course, I want to do nothing perfectly out here if I'm really trying to do addressing. And these guys can also jitter around by the maximum amount and do nothing. So I want this kind of top hat response. Well, we just saw that the NMR crowd were able to design these kinds of composite pulses, and so can we. And basically, the way we chose to do it was we wanted to keep the amplitude of our microwaves constant and just modulate the phase. So basically what we have is a situation, you design a control waveform that leaves the atom and spin down outside a certain frequency interval and flip them to spin up perfectly inside a certain frequency interval. Now here's the phase modulation waveform that the computer spits out. Why does it look like that? I'm not sure. This is certainly not unique either. You could come up with other waveforms that have this kind of top hat response in frequency. This is data, by the way. So we can do that. It's actually relatively straightforward once you set up the necessary software and so on to do these pulse optimizations.
So this looks like a very complicated pulse. And do you have anything in your software which tells you I want to make a pulse which is as simple as possible, or does it not matter really for you guys?
It does not matter, because ultimately what we have is a waveform, just, samples, numbers as a function of time that goes into an arbitrary waveform generator that can phase modulate.
So it doesn't matter? It can be...
No. We don't even have to ever look at this.
So you don't turn the knobs by hand anymore?
No. This kind of thing after the advent of arbitrary waveform generators that can make waveforms with direct digital synthesis. This is just super easy.
Okay.
You might as well be doing theory.
What do you mean?
I mean, you don't have to turn any knobs. That's really what I mean.
It was meant to be a pejorative comment.
No, it was actually meant to say that once you have simplified things so much that you don't turn knobs anymore, you have essentially become a theorist. You know, and I think the NMR crowd would admit to this too.
Now, do you, well, obviously you set, for example, how many different phase steps you're going to allow.
Mm-hmm.
So what would happen if it were half as many?
If you make it too short, you don't have enough free parameters to ensure that you get the right shape.
So it just fails.
It just fails, yeah. That's right.
And how good is that when we can't tell from fluorescence signal as to what the fidelity is for making the population inversion?
I will show you experimental data if I can get to it, but
Certainly if you questions.
yeah. Well, if you keep asking questions, we'll have to defer this, I think, to the lab visit. But the fidelities are in the high 90s.
Okay.
Right. So here's the pop pattern response. How does it work? Well, as you can see, it's not intuitive, right? But let's pick some points along here, and let's make a little movie of what the block vectors do during the pulse at these different points, just for fun. You can see that they move in different and rather non-intuitive ways. They wave around, and then at the very end, must be they just end up like that. It's because they all evolve under different effective detunings, because they sit at different points in this tuning or addressing lattice.
Now, do you specify a region over which you don't care what happens?
No.
Because there's a kind of a slope to that.
Yeah.
And you would think that, you know, making that slope smaller might be, make it easier on the...
Yeah. So the steepness of this slope has to do with the bandwidth of the pulse. And that's essentially related to 1 over the time duration over which the phase is held constant. Right. Sorry, no, the other way. The steepness of this slope is the bandwidth of the pulse, which is related to the overall duration of the whole sequence. That's right. This width here is the duration, is proportional, inversely proportional to the duration of the individual pieces of the pulse. So we could make a longer pulse and make this sharper. That's the only way of doing that. So we were limited by the coherence time in our optical lattices in terms of how far we could go.
So it's still trying to make, for example, things at 583. It's trying to make that a pi pulse, and fails. It
fails. It can't make a pi pulse at one point and an identity at a point immediately next to it. It's just not possible.
Right.
So it just optimizes some cost function.
Right, but the cost function is, it still costs something to not have a pi pulse.
It does. Okay. So, and what we're doing, of course, with our superlattice that we've applied is this frequency dependence get mapped into precision. So what we can do is we can do a robust spin flip where this guy here started, we have 3 in neighboring sites, this guy started to spin down and gets flipped and spin up. These 2 guys don't do anything. And here's data. Here's 3 atoms prepared at neighboring sites and read out with resonance imaging. Here we've applied the robust pulse to the guy in the middle. We should of course compare that to what happens if we apply the same spin flip pulse that we used to make these guys in the first place. So just a plain pulse. Actually, it has a Gaussian time. It has a Gaussian time dependence and frequency dependence, just to avoid wide tails. But, what we see is that the plain pulse doesn't work as well, because that's perfectly resonant only for atoms right at the center of this distribution. But the atoms that sit out at the side here, because they don't sit at quite the right place in the addressing lattice and never don't have the right frequency, that simple pulse don't work very well for them. But the composite pulse works perfect. You could look at a plain pulse, you could make it more intense and shorter so that its bandwidth increased, and then you can certainly flip all these guys But when you do, you get something like this blue curve where you start flipping the neighbors as well. Right, so the top hat response really helps you be robust. You can touch the center guy without touching the neighbors. And that's really, I think, the key of this experiment. And if Pierre would like me to stop now, I can, or I can go on just for a couple more minutes.
I think it's probably a good time to stop because it leaves us a bit of time for questions.
Okay.
And then you have another lecture. Are you staying today or at all, or you have to go back?
You know, the problem is that our dean has his retirement celebration at the university at 2 p.m.
right.
and I have to be down there for that, or somebody's going to kill me.
So
So
it's no longer dean, so who cares?
you obviously have forgotten about Bobby Duss. You know, I'll stay as long as I can. I'll probably have to leave around 12:30.
Okay.
But I will be around during the lab visits tomorrow.
Okay.
You know, and available for as much discussion as anyone would like.
Okay, well, thank you so much. So we do have